Hello, this is Raf Alvarado and welcome to Exploratory Text Analytics. In this video, we're going to talk about the concept of entropy. So recall in our previous video regarding information theory, a message is just a sequence of symbol instances of a given length selected from a symbol set and produced by a source. In other words, a message is a minimal definition of a text. Now, the interesting thing, and this is Shannon's great insight, is to view a message also as an event drawn from a sample space associated with that source. And here we're just using the concept of event and sample space as defined by traditional probability theory and statistics. An event is one possible outcome in a sample space which defines all possible outcomes. Now, Shannon's intuition is that the amount of information in a message is related to its probability relative to that sample space. You could put this another way and say that Shannon is defining information in terms of probability. So we saw that the amount of information in a message might be modeled as the log of all possible messages from its source. Now, this would be true if all symbols are equally possible and independent, which was the case in the Library of Babel. But we know that in a language like English and all natural languages, not all messages are allowable. In fact, it's a tiny subset relative to the whole that is allowable. And the selection of these messages is governed by the constraints of a language model of the source. So we need another formula. And our new formula is going to describe a property of the language model as well as of the messages produced by that language model. So to solve this problem, Shannon develops the concept of entropy. Entropy measures the amount of uncertainty in probability distributions or probability mass functions. So to get an intuition of the concept of entropy, consider the following three simple language models for a symbol set. And we're thinking of an alphabet that has 4 letters in it. So you can see how they differ in the uncertainty they possess. Imagine the one on the left where every letter has equal probability. That's again the Library of Babel. You can see that there's high uncertainty in predicting which letter will be selected from this sample space when you're trying to interpret a message coming from that sample space. In other words, think of this as you're betting and you want to put your money down on A1, A2, A3, or A4, and you're eagerly waiting for this source to produce a character. What are you going to bet on? So in the left-hand case, we have high uncertainty because every letter is equally probable. So you really can't bet very effectively in that environment. In the second case, we have medium uncertainty, and here we see that if you're betting, you're probably going to bet on A2 because it happens half the time. A3 and A4 happen an eighth of the time each, so they're less likely to be voted on. And on the right, you see the lowest uncertainty, which is the same as saying the highest certainty, where you have clearly one example, A3, one letter, that's always going to be the case. So if you're betting and someone's dumb enough to let you put down money, you're going to bet on A3 because it wins every single time. So the idea of entropy is to provide a way of characterizing this intuition that a probability distribution itself has some overall sense of uncertainty, some overall quality of uncertainty. So let's look at the formula that Shannon comes up with. We'll look at the first one here. The entropy of a random variable, and a random variable can be thought of as a information source, is equal to the negative sum of the probability of a message coming from that source times the log of that probability. And we choose 2 as the root of our log because we want our entropy to be expressed in bits, because bits are the elementary way of thinking about information. It's the simplest kind of alphabet you can think of, a choice between 2 characters. Another way to express this that you'll often see is that the entropy will be expressed not as a negative, but as the log of the inverse of the probability. because the log of a number less than 1 is a negative value, and so you don't need the negative there, and that's basically all that negative did in the first place. In some ways, this is more intuitive because, as I'll show you in a second, the inverse of the probability is an interesting number to consider. The entropy can also be considered just to be the expected value of a distribution, where the function that's being applied to the probability is log 2 p of x. And oftentimes you'll just see entropy expressed this way. H of p, which is the probability distribution, equals the sum of p log 2 p. That actually should have a negative in front of it. So this is all very straightforward. So the first two formula are the ones I want you to consider. So looking at the second formula, here's an intuitive way, perhaps, of understanding it. The first element of the formula within the sum is just the probability of the event. So that's very important, obviously. The entropy is related to the sum of probabilities times some function. If you just sum the probabilities by themselves, you just get 1. So that's not very useful, right? So what you're doing is you're multiplying it by some interesting factor. That's what the expectation function tells you. That interesting factor is this. Just look at the right-hand side. The factor that we're multiplying the probability by is its inverse, which is an interesting number because it tells you the amount of uncertainty, the factor by which knowledge of the event reduces the uncertainty of the event. So if you know that a letter is, like, for example, if you're trying to anticipate the next letter of a word in English, if the letter E comes across the transom, that reduces your uncertainty by a little bit because E is very common. But if the letter Q comes across, that reduces your uncertainty by a lot because that's a relatively rare letter, and it gives you a lot of information about what might be coming next. So the probability of Q is lower than the probability of E. Therefore, the inverse of those probabilities represent the factor of uncertainty that it reduces in the message. And then, of course, the log 2 is a way of expressing that uncertainty, which grows exponentially in a linear fashion and in terms of bits, which is how we want to express things when we're working with text. So here's an example drawn from Manning and Schutz, the book, to get a sense of how we think of entropy. So let's take the example of an 8-sided die. So that means that every side is equally probable. That's an example of what we were calling a very high uncertainty distribution, very high entropy distribution. Actually, that would be a low entropy distribution. And so let's look at what this turns out to be. So the entropy of x equals, for each side, we multiply its probability by its log. And that just means we do this 8 times. 1/8 times log of 1/8 equals negative log of 1/8 equals log of 8 equals 3 bits. So that an 8-sided die then has an entropy of 3. All right. And what that means is you can translate, the entropy becomes an interesting concept for communication theory because it provides you with a metric with which you can recode the messages produced from a certain information source. So here, from this information source, we're going to need 3 bits, a message of 3 bits long to encode all the results that are produced from it. And here you see that encoding scheme written down below. So here we have a simple case of a 2-sign system, 0 and 1. And on the x-axis, you see the probability of one of those elements of 1. And if the probability of 1 is 0, you end up with very low entropy, 0 entropy. And if the probability of 1 is 1, then you end up with high entropy, the same thing, low entropy. And it's only in the middle where they're equally probable that you get the maximum entropy. So this is a way of thinking about entropy as a distribution. So here's another example, but we're looking more at a language-like situation where we have an uneven distribution associated with the symbols in the symbol set. This is something called simplified Polynesian. This again is from Manning and Schutz. And here we have a set of letters, some consonants and some vowels, and we have probability distributions associated with each. So if you compute the entropy of this distribution, you end up with a smaller value. So the entropy is lower because there's more certainty here in the sense that it's a little more lumpy. The letter A and the letters T are more frequent than the others. So this creates a more skewed, if you will, a lumpy distribution. That means that the entropy is going to be lower. So what this also means is that you can design a coding scheme that takes advantage of the fact that the average message length is less than 3. So that means that some of your letters might be encoded with just 2 characters or 2 bits. So here we see below the letters T and A, which are the most frequent, are encoded with only 2 characters, whereas the other letters are encoded with 3. Here's another way of thinking about entropy as the number of decisions it requires to get to a certain outcome. Another way of thinking about this is the number of questions that are required to ask in order to guess a message. So here we have a case where 0 and 1 are equally probable. So if you wanted to look at, see what the outcome for any given message is, here we have 0, 0, 0, all the way up to 1, 1, 1. You'll see that in each case, it takes 3 steps to get there. And that's a way of thinking about entropy having a value of 3. So entropy stands for the encoding length. Here we see 3 numbers are required to encode each outcome, but it's also the number of decisions that are made to produce that. So remember that a bit is not really a character. It is expressed as a character. It's really a choice of characters. So when we say that there's 1 bit of information, what we're saying is that there's 1 choice that was made, 1 selection, 1 decision. Here's an example of a distribution of where, look at the number 0, 1, 1 here. It's marked off in squares, where we have a distribution that's uneven, where we're saying that the probability of 0 is 0.4 and the probability of 1 is 0.6. So that means that it's more likely in each case to be 0.6. So that as we create a longer string, our probability distributions vary. So you can see that the most likely string from this language model is 1, 1, 1, because 1 is the more probable choice. But doesn't mean that you're not going to get these other strings as well. You have, a 0.14 probability for getting 011 and for getting 010 and for getting, let me see what that is, 110. And the lowest probability string is going to be 000 because, of course, 0 is less probable than 1. This shows all the possible outcomes of this language model for producing a message of length 3. And we see that it has an entropy of 2.7. Again, that relates to the number of characters on average needed to encode the outcome, as well as the average number of decisions made necessary to predict the outcome. So the difference between Babel and English is the entropy of the symbol distribution. In Babel, every symbol is equally possible. It has what we call maximum entropy. In English and other natural languages, symbols are governed by a probability function that has a lower entropy value. In Babel, one cannot predict the symbols in a message. In English, you can. So here's some ways to think about entropy. Entropy is a property of the probability distribution of a random variable. As we mentioned before, it's really about the distribution itself, even though there is a concept of self-entropy. It's a degree of uncertainty. You can, as we've said, it's a measure of uncertainty in a random variable. We can also think about it as the degree of what I call equiprobability. How equally probable is the distribution? So maximum entropy means that every every outcome is equally probable. You can also think of it, many have described it as minimum message length of recoded messages. So if you could optimally recode your messages using entropy, you would come up with the minimum message length of those messages. It's the average number of decisions to produce an outcome. You can think of it as the size of the search space of possible values. And some call it surprisal, like how surprised are we to get at a result? So again, looking at English, if you're trying to predict the next letter in a word, you're not going to be surprised if it's an E, but you're going to be more surprised if it's a Z or a Q. This is a word that's very common. This is a way of expressing entropy that's very common, but I think it's a little bit too psychological in the sense that, according to this, you should be really surprised at every outcome of a distribution that has maximum entropy. And in fact, I think psychologically it's the opposite. You're not surprised at all because it's all random. So I think that that's actually not as useful as it might be, but one gets the idea. So entropy is also a metric that's sensitive to symbol set size. So you'll get different entropies for different systems with different symbol set sizes. So maximum entropy in a symbol in the case of a die is going to be 1. In the case of a coin, it's going to be 2.59. But you want to think about these things as in some sense being the same. So we have a normalizing measure for that, and it's called redundancy. So the redundancy of a language model or a random variable is 1 minus the actual entropy over the maximum entropy. So you can see that if the actual entropy equals maximum entropy, then your redundancy is going to be 0. That means every message produced by that system is unique. For example, English is 50% redundant. This is one way of showing the redundancy of English, the fact that you can read sentences without some of the characters present. Here we have half of the characters missing. Actually, it's basically all the vowels are missing. For example, I bet you can read this. Morse code reflects this. This is an encoding scheme that was developed obviously before the development of information theory, but which reflects the core intuition that high frequency symbols don't need to be encoded with message lengths or with the same number of characters, and low frequency members of the symbol set can be encoded with longer sequences. So entropy is often called Shannon entropy to distinguish it from the entropy of physics, although many have shown that the two are related and indeed part of this very same phenomenon. Entropy and information are often regarded as synonyms as well, but it's important to understand that they're not. They are opposites of each other. In a decision tree, for example, when you talk about information gain, you're talking about the reduction of entropy or the reduction of uncertainty. Stone, in the little article that I asked you to read about information theory, describes them as opposite sides of the same coin. They're sort of warp and woof. They're co-defined, but they have opposite meaning. Also, I would point out too that the word information is overloaded. It has many distinct meanings related to entropy, as we now have given Shannon, but it also means form, it means news, it means lots of different things. And I would suggest that you read information or Shannon information as a new definition of the word information that trains our attention on the importance of probability for decoding messages. So what's the importance to text analytics? Aside from a solution to the problems of communication, the concept of entropy provides a way to think about text detached from the situation that we saw with recur. Remember, a text is a message, it's an utterance that has been detached from its situation. And so we're stuck with the message itself and its internal properties for interpreting it. This approach to thinking about text by Shannon helps us come up with observations and inferences about the message independently of having to talk about what it originally referred to. Now, doesn't mean that we can't introduce speculations about what a message refers to based on our knowledge of its situation of utterance. But this provides us with a hard quantitative way of describing a message that we can then relate to those softer, more qualitative observations. So natural language processing relies heavily on the concept of entropy and Shannon's theorems. And as we're going to see from Jurafsky and Martin's book, the chapter on n-gram models, language models, is essentially an extension of what Shannon argues in this paper.